Good afternoon, everyone. Today we are really pleased to have Professor Mengye Ren from New York University to be our webinar speaker. Mengye is an assistant professor of computer science and data science in Huron Institute of Mathematical Science. Mengye received his Ph.D. in 2021 in computer science from the University of Toronto. Even with his young age, Mengye has already a lot of industry experience. Before joining NYU, he was a visiting faculty researcher at Google Brain. And from 2017 to 2021, he was also a senior research scientist at Uber Advanced Technologies Groups and Waabi, working on self-driving vehicles. So this industry experience kind of explains his unique perspective on his research. Mengye's research focuses on making machine learning more natural and human-like in order for AIs to continue learn, adapt, and reason in naturalistic environments. And his research area includes machine learning, computer vision, representation learning, meta learning, few-shot learning, brain and cognitive inspired learning, robot learning, and self-driving vehicles. And today he's going to tell us about lifelong learning in structured environments. Let's welcome Mengye.
Thank you so much, Zhihua, for the great introduction. It's my great pleasure to be here to share about some of our works in the area of lifelong learning. So I guess everyone here is pretty familiar with machine learning and how successful they are these days. So typically we are when we apply machine learning in the real world, we're essentially building a very classic pipeline, starting from defining, say, input and outputs, and we collect lots of input data from internet or other real world data sets. And then depending on the nature of the algorithm, you might want to choose to annotate a bunch of the data and do some cleaning and relabeling to make sure this data is curated in a very nice format. And then you train a model or a deep network to predict the data. And this basically is the full cycle of how you would deploy a machine learning model. So this becomes really tedious and having a lot of manual steps, but also it's very inflexible once you deploy this model. For example, if you want to apply this model to a new environment, or all of a sudden you have a new class label that you want to add to your output, then it becomes really inflexible, where you have to perhaps redo your data collection again and retrain the entire model. And some of the bigger models these days needs an abundant of resource to be trained on, so it's not that easy to retrain an entire network. And people may find that these days, like a lot of people talking about foundation models and large language models, and they seems to have pretty good ability to adapt to new things, right? But however, like no matter how much data they have been trained on, right, there always be knowledge holes in their systems, and they need to be continuously adapted. So this is an example that I tried recently with, for example, DALL-E 3, right? So I asking it to generate images of a watch showing at 1 o'clock, and then you can replace this 1 o'clock to any other time, right? And I also add another sentence: be careful where the watch hands are pointing, right? So as you can see in the images, and you can try this yourself today on OpenAI website, right? All the images giving me really nice looking watches and stopwatches and so on, but none of those are really showing at 1 o'clock, right? So this is already a really amazing progress for generative models, but somehow it's not getting the concept of 1 o'clock, despite having seen so many clock images or watch images online, right? And to probe this problem a little deeper, right, if you do a Google search, right, on any consumer product, any watches, smartwatch, or anything like that, you'll find a picture like this. So what essentially happened is that all consumer brands, they choose to advertise their watch at the time of 10 past 10. So this is kind of a canonical like time for anyone who wants to advertise a watch. And the reason being is probably a little bit more visually appealing than other times, right? So it's like upward and then kind of left and right symmetry going on. And because there's so much data imbalance in the training data, the model basically failed to get the concept that the time, where the position the watch hands are pointing are correlated with time. They thought maybe this is just part of the watch concept that all the watch hands needs to point in this way. So this is what I'm saying, like despite the amount of data these models are trained on, right? Like it's not gonna like generalize to every possible knowledge out there. And there is a need, say, to continually adapt these models so that we can keep their knowledge up to date or teach them correct new knowledge. For example, in this case, we may want to teach DALI 3 or a foundation model, how to recognize a clock. But then in order to do that, these days, we will have to recollect a bunch of watch images with the correct time, and that's not correlated with the time of 10 past 10, right? So these are still not really feasible these days. And people may argue that some of the in-context learning are showing really good promise these days, right? But I would say that infinite contextless is just not going to be really sustainable. You can't just put all the new knowledge into your prompt or context. So this motivates us from this paradigm of learning from a real world agents, right? So humans are examples of real world agents, right? From little toddlers to adults, we are continuously adapting ourselves to new environments and essentially learning in an open world, right? We're not saying having a data sets to start with, we're actually collecting our own data sets. And when we encounter new concept, we memorize them and then generalize to more and more new concepts through this online experience. And I think this is a really essential feature that's currently still lacking in large-scale machine learning or any classic machine learning paradigms. And so there has been this area called lifelong learning. It's a sort of an umbrella term that tries to capture all of these desired properties that I just mentioned. Right. So in essence, lifelong learning means that we want to learn multiple tasks, skills, and source of knowledge in a sequential stream, right? And we want to be able to continually improve on each task and even transfer between tasks. So like maybe learning on one of the tasks is going to improve you on the other, compared to just learning each task individually. And so the concept of lifelong learning is instantiated in a bunch of more well-defined learning paradigms. Right? For example, continual learning, online learning, or fusion learning, which I'll go into more details of these individual paradigms later. Right, but it's so lifelong learning, the concept is more of an abstract concept, but people have tried in the past to define it into more concrete mathematically well-defined learning scenarios. And one thing to mention here is the comparison between lifelong learning versus sort of evolutionary learning or meta learning, right? So if you can compare these, right, lifelong learning refers to a learning from the lifetime of an agent. So a lot of the actions or states can only be visited once. Right? Whereas evolutionary learning and meta learning, you basically have a bunch of rollouts. You can launch up lots of agents, starting from scratch and learning all the way till the end. Right. So basically, this is more of a kind of like a meta learning where you can learn the learning algorithm in the outer loop, and in the inner loop, you do some simpler form of learning. So I think on the fundamental level, these two concepts are very connected, and a lot of the algorithms do share the similarity. But lifelong learning emphasize more on the transient properties, right? So you can't have infinite data or infinite simulation. You can only leverage the data that's available to each individual agents out there. Is there a, oh, okay, so this is your message. So there's a question. All right, so for lifelong learning, there are lots of potential applications, right? So robots is definitely one of the most obvious application out there, right? So robots like self-driving cars, right, or home robots. Basically, like when a product is finished, it hasn't experienced all kind of road situations or home environments, right? It still needs like continuously need to adapt itself, right? For example, maybe the self-driving car enters like a wild area or some unknown road sign that's showing some form of danger. Would it be able to quickly reason about the situation and learn about this new condition, right? And for outside of the robotics area, right? So there's also augmented reality. For example, you can basically have a smart glass that you wear all the time. And this smart glass is going to have a camera that looks at your visual scene, that everything you see in the real world. And what's going to be interesting is that maybe the smart glass can learn through your own visual experience, right? So this will be enabled by lifelong learning. Ideally, you wouldn't want to share your own personal, private visual data with anybody else, right? So you wouldn't want to run large-scale machine learning that combines everyone's individual visual experience. But you actually would want to have a learning algorithm that learns through your visual experience so that it can, say, help you remember the past events, or maybe just like help you do personal assistance. And also this not only covers in the vision domain, but also the language domain, right? So you can have a personal assistance chatbots that learns through your conversations, right? And learn some new concepts that's only maybe you know better, so that it's not just a generic chatbot out there, it's actually customized for your own needs. So I think there's lots of personalized applications or robotics applications for lifelong learning, but the algorithm is still are very much in the early stage that people haven't explored these exciting areas yet. So one of the special case of lifelong learning is called continual learning, right? So basically, how it's defined is that you have a sequence of tasks and you cannot look back in the past. So you basically start with task one and you have your algorithm learn a bunch of data sets on task one and then transition to task two. Now, the constraint is that at task two, you cannot look back in task one. Right, so some algorithm may leverage a memory buffer where you can store some of the examples in the memory buffer so that it can look some of the examples in the past. But the idea is that this memory buffer is a limited size so that you cannot possibly store whole data sets in there, right? Otherwise, it would be just same as if you do learning in the IID situation. So lots of applications for continual learning, right? For example, social media tech companies want to say like train new models on the newest social media posts or new contents, short videos, products, etc. Right? But on the other hand, they don't want to retrain the entire model, which may take days or not, if not weeks. Right? So this continual learning is gonna make the whole updating process much more efficient. And there are lots of approaches. I'm not gonna go into the details of how you do continual learning in today's talk, but say you can regularize your model so that they don't deviate too much in each task. You can also say do replay, where store some of the examples in the past. And there's also architectural changes that you can make to the model so that it only activates, say, part of the network so that they don't forget as much. And one of the sub-problem of continual learning is something called incremental class learning, where each task is basically you're learning a few new classes. And in the end, so say you learn 2 classes in one of the tasks, and in the end, you get an 8-way classifier of a multi-class classification setting, right? So, and transfer learning is another example of a continual learning, which looks at 2 tasks, and then you start with task 1, and then you do task 2, but you want to see how much task 1 can be transferred into solving task 2 compared to just train task 2 from the beginning. Okay, so these are all some sort of the high level description of what continual learning is. So the downside of continual learning is it can be pretty rigid and less naturalistic. So as I said, the industry may care a lot about continual learning to make their retraining more efficient, right? But in the real life, as a real world agent, like robots or human, you don't necessarily see the world like this, right? So you're not like going to your office once in your lifetime and then going to say like on the street and you never revisit your office again. It's more often like you go into one environment, into another, and then revisit some of the older environment. So that's probably a less a natural representation of what you would see in real world. And the other related paradigm is called future learning, which is something I had worked on quite a bit in the past few years. So future learning focus on learning from only a few examples, right? So before in continual learning, each task you still present tens of thousands of examples, right? But in contrast, humans, we continually learn new concepts or skills with only a few examples. If you show me what is a scooter in the first time of my life, right? I'm gonna learn what that object is. Even though I have never seen that, I could think of that as a transportation tool that has 2 wheels and going to allow me to walk faster as if it's a bike, right? So this type of quick, rapid learning ability is something that humans excels, right? And so there has been also a lot of future learning techniques, right? So one of the major paradigm there is something called a meta learning, right? So basically at training time, you're going to solve a bunch of those future learning tasks. So each task is going to be having a training set of like a few training images, and also you're going to be tested on a few test images. So the idea is that you want to be able to train networks that can learn with just a few training images and do well on test images. And this typically works pretty nicely, right? But overall, this paradigm is still really far from the type of lifelong learning that we want to study, right? Because the network is just going to throw away everything else and then focus on learning a new task containing 5 to 10 examples or even 1 example. But this such network is not going to be useful, right, when you try to incrementally accumulate your knowledge, right? So it only studies basically a sub-problem in the lifelong learning challenge. Right, so as we talk about the challenges of lifelong learning, so basically there are a few of these challenges, right? So first of all is related to, incremental learning, right? How do we grow our size of the outputs? And remember, this is not like we're growing this like a uniform distribution, because oftentimes we're basically growing our outputs in a long tail distribution. For example, most of the cars you see on the road are going to be, say, like taxis or regular small vehicles or buses, but maybe once in a while you're going to see like emergency vehicles, right? So this basically needs you to grow your size of the outputs by observing these very few examples. So in this sense, it is also related to future learning. And here we basically need memory and incremental learning algorithms to address this challenge. The second one is changing distribution over time, right, which is related to continual learning that I talked about, right? So there's also transfer learning, domain adaptation, and all kinds of techniques that aims to address part of this problem. And the third one is probably more recent, right? So like in self-supervised learning or like models like transformer large language model, right? Basically what they operate on is a context window, right? So for continual learning, the challenge that is that the context window is pretty small and all the data there in the context window is correlated. So basically what you want is, say, have a replay buffer that looks at other examples in the past so that you don't have to deal with the small context window problem. So there are quite many challenges with lifelong learning, and each of the individual one is actually like a subfield of machine learning. So that's all for the background of today's talk. And today in the agenda is that I'm gonna show you some of our work, starting from a work from 2 years ago, which on the topic of incremental concept learning, which is an effort to combine continual learning and few-shot learning in a one learning paradigm. And there we show that we can have a memory module that basically accumulates the new knowledge. And such memory module can work end-to-end with the backbone network that provides the representation. And we also show a follow-up work that can be used for self-supervised learning, meaning that although the concepts are being incremented, right, we're not giving actual labels. So the network itself kind of do its own clustering on these concepts. And then we will move on to some of the more recent works, right? So it's nice that we can come up with a more naturalistic learning paradigm, but in order to study it and understanding it more deeply, here we actually study a more simpler paradigm. And this is what we call as interleaving learning. So it's actually different from the traditional continual learning where you have a task 1 and task 2, and then you never look back at task 1 once you leave task 1, right? So actually we actually have task 1 and 2 and then interleave from each other. Okay, so you basically start 1 and 2 and then go back to 1 again and 2 again. And then you can extend it to multiple tasks. And I'm going to talk about a couple interesting phenomena there. And lastly, I want to talk a little bit on the safety side of lifelong learning. And this is basically the biggest concern about lifelong learning is that you don't want to deploy it in real system because it's going to change your models all the time. How are you going to be sure it's safe, right? So here we don't have like a very comprehensive answer, but I'm going to show you some work that shows up some interesting phenomena in that area. So on the topic of the first thing in today's agenda, right? So what we're proposing here is a learning paradigm that combines few-shot learning and continual learning. So as I said, lifelong learning, you have to increment your learned concepts, right? But also the newly learned concept needs to be supported just by a few examples, right? So because, for example, one day you see like emergency vehicles on the street, you want to be able to quickly remember that, right? So for example, your agent wander in the kitchen, right? So maybe you look at some of the new classes that you haven't seen before, right? So maybe this is a cup, right? So this is class label number 1 and a plain class label number 2. And maybe sometimes you don't provide the class label, so the dash line is like the world doesn't give you a class label, but you guessed it is one, right? And so basically your agent is going through this sequence of learning and every input of the sequence is just one example. And in the end, you are going to output some answer online and then you are going to be evaluated on the total accuracy. And we can even have another layer of complexity where you have a context switching. After one environment of the sequence, you can enter the office and the living room and then the office again. So basically, this is a higher layer of how the agent is doing continual learning. Right, so to address this problem, what we propose here is a memory network that we call the contextual prototypical memory, right? So the first is a convolutional neural net that provides the visual representations or features, and then these features are being aggregated into a short-term memory, right? Here we used a recurrent neural network, but you can imagine in today's context, you could replace it with a transformer network which can also encode the context pretty well. And lastly, we have a prototype memory, which is sort of like a semantic memory that holds on to the classes that you just learned with just a prototype vector. So a prototype means the centroid vector of that class. So basically, if a class has multiple examples, then we can basically do some sort of averaging here to remember the centroid as well as the width or radius of that centroid. So this is a more compressed expression of what we have learned in the past, right? And we can keep aggregating new information into this memory. So how it works is that during training, we're going to present many of these learning episodes, and each episode has a sequence of objects, and basically the network has to produce an online answer what this class of object is, right? And it's going to be trained to maximize the performance on the training data. And test time, you're going to look at a sequence of new objects which you have never seen before, and you actually don't care whether this is a semantic class of a shoe or not. It's just you're going to internally increment your concept space, right? And so basically this is how it works, right? So at test time is just as same as training time, where a network is making some online learning and decisions. And I should mention there should be other forms that you can design this memory, right? So trying to aggregate in the prototypes is definitely one choice that we found to work really, really well. But you can also imagine you have a whole recurrent neural networks that's trying to hold up this concept. Or maybe you can have some of the layers that doing gradient descent that tries to learn the new concept, right? And you can also have a memory that's distributed among different layers. So definitely this is a more complicated solution there. So we actually compared to some of those, and one of the experiments we ran is for omniglot handwritten characters. So these are all handwritten digits from lots of human languages. And basically what we did is that we put all these images into a sequence so that the network can learn through this sequence, but also different characters may form different environments on a higher level. So you might want to say like doing a more hierarchical memory organization. And we compare to some of the memory networks that I just showed you, and including some gradient-based learning, right? So, and like some of the metric-based prototypical network, and the recurrent net-based, which is called a differentiable neural computer. And our methods works the best here in terms of the accuracy of outputting the class of the newly seen objects. And to project it into a more realistic environment, we're testing here as a home environment where the task here is to recognize new objects in new homes, right? So basically we're training this learning algorithm a bunch of home environments and testing it on another set of home environments. And you can see it's doing pretty well. It's able to predict unknown, right, for the first time, and then for the next time, it's able to memorize what this object is. So you can imagine an extension of this algorithm can be really useful for a home robot or for like a personal assistance in home environment. And to extend this work a little bit more, right? So few-shot learning is really nice that you can learn concept with just one examples, but oftentimes we probably don't even need label data at all, right? So basically when you're wandering in a supermarket or grocery store, right? So you look at items are being grouped, organized well on the shelf, you kind of know that all these items are belonging to one category. So the fact that our brain can basically visually group similar items together, so also motivates us that maybe we can design something that's completely unsupervised. And the sense that categories also should emerge by grouping these items together. So some early psychology literature actually studied this, but back in the days, there were no representation learning. So basically the inputs a bunch of features already, and then you're just doing some online grouping of these features. But we actually show that you can combine this with a network that's starting from random, right? So one of the interesting things that we want to study this is because we want to apply this on egocentric videos, right? So egocentric videos is just videos that basically, for example, a car camera or a head-mounted camera from a baby's point of view, right? Basically, there are no like object annotations whatsoever, right? So each frame may contain an object, may not contain a center objects, but we want to have the network to be able to learn directly from the video data so that it can group similar items together. So that's kind of the motivation. So we adapt a similar model from before. We take out the recurrent nets for simplicity. So basically, this is a convolutional net that hasn't been trained before. So all its training signal are from those egocentric video streams, right? And then we're going to put the feature vectors into this prototype memory. And basically, the idea is that the clusters are stored in the prototype memory, and the smallest cluster are being recycled, right? So this is basically a streaming memory. If all clusters are far away from the current input, then we create a new cluster. So this is basically an online clustering algorithm, right? Similar as before, except that there's no input labels, right? And on top of this online clustering algorithm, we also introduce a learning objective that's from the self-supervised learning literature, where we basically want to augment the same image from before. So for example, this one, we do a random cropping or random color jittering on this image, and then send it into this network again. And what we want to be able to say is that the augmented view should still be in the same cluster. So this creates the learning objective. And of course, you want to control the marginal probability of creating new clusters, because otherwise you may end up with just a huge giant cluster that captures everything, or have each individual frame creating their own cluster. And either case is not very ideal. So these are the learning environments. Two of those I introduced before, and this is the hand-mounted camera from baby's perspective. And I thought it's a really interesting one. It's also it's an interesting psychology question, right? So how does the visual representation emerge from our point of view? And this features an online and non-IID setting, right? So we're streaming a very small number of video frames every single step, and then we're moving towards the next context window. And some of these are evaluation metrics. We're looking at how well you can basically cluster them, right? And how these cluster corresponds to the actual clusters that we defined, that we have labels on. And then we can also do a supervised clustering at the end, basically to evaluate how good the representations are. Right. So what's interesting here is that for the first two environments, right, basically this unsupervised algorithm is able to almost match with the supervised performance. And this really encouraged us, right? So like, although these are simpler environments, right, the fact that this algorithm doesn't actually need class label is actually really encouraging. And on the third environment, which is the baby head-mounted camera environment, we also were able to get superior results compared to other self-supervised learning methods, but also getting closer to a network, say, that is pre-trained on ImageNet, whereas our network hasn't seen any ImageNet images from the internet. It has been solely trained on this video setting. And then another upper bound here is another self-supervised method that's trained on the videos, but they have IID learning, basically have a huge memory buffer that shuffles all the video frames all together. And so this highlights the challenge we are facing with this online and non-IID setting. And one way to ablate this effect is to study the batch size, right? So what we can see is that with a small enough batch size, our method is basically the best across the board, whereas other methods, self-supervised learning methods, are getting better and better with increasing number of images in your batch. Right, so increasing the batch size is making more like an IID setting. Right, so the reason being is that we think that our online clustering is helping with this non-IID nature, right? Because we don't really care about each cluster having the same size, right? As long as it's something new, we're going to increment a new cluster. Whereas some of the self-supervised approach, they're assuming that you have a data set of like say 100 classes and each one has equal number of images. So that assumption actually was baked into some of the baseline methods. So by removing that assumption, we were able to do better in this more naturalistic learning environment. So there's something else I want to mention about is the visual learning from lifelong videos. So what I just talked about is basically the top two where we incrementally grow our memory, right? The classes are incrementally grown, right? And we keep adding new classes together. And in case there are non-labels, we're going to group those input images into new instances, categories, or even environments. So this is kind of a pyramid of components that what we need for visual learning in the wild for these lifelong videos. But the challenge here is that a lot of videos, they're pretty high resolution. They don't only contain a single object. They can be really crowded, lots of objects moving all the time, right? So it's another challenge that we want to learn from the unlabeled raw video. So this is more of from the perspective of computer vision, not necessarily for general learning, but this is something that we need to worry about. So in this, one of the papers that we have on ICCV 2021, this is Yuan is the first author on this work. And basically we did a very simple approach that worked extremely well on video representation learning. And the idea is that regions that move together should contain consistent representations. So for example, this car that moves a little bit to the front, right? Despite its movement, the features of this region should look similar to the feature of that region. And basically in the representation space, we can make sure the features are equivariant. Basically, they move the same way as if they do the same way in the pixel space. And then we use this as a self-supervised representation learning objective, as opposed to have describe the entire image to be similar to this one, which can be prone to a lot of the movement errors. So here's a visualization that we pre-trained this on a large-scale unlabeled video data set. And then we read out this on cityscape data set, which is semantic segmentation. And we use only a linear convolutional layer to read the representations out. And you can see the representation actually are really good at classifying different regions. So this is a lot of excitement there, but this work, we still need to have some sort of optical flow from a standalone network that can predict the optical flow. So for semi-supervised learning, we can also give the network just a little bit of labeled images, and you can see how it can be much better compared to networks that only train on labeled images, right? So this really showcased that the representation learned from raw unlabeled videos are giving a lot of benefits. And there's another recent work by my colleagues, Adrian. So he basically introduced a network that combines the motion learning and content learning all together, right? So the motion here, which is producing the optical flow, can also be learned without any labels. So the entire framework can be learned on videos and images with no class labels, which is really encouraging here. So just an interim summary before I jump to the next parts, right? So here I introduced a lot of memory mechanisms for incremental class learning from a stream of instances, images, video frames, and so on. right? So the memory module can support unsupervised representation learning as well, right? So everything just backprop end to end. So for video representations, I think one of the key is to leverage low-level pixel motion, right? And so building all together, I think this will be a feasible pipeline for learning representations in the wild for egocentric videos. But what we have so far have done is to make it more and more naturalistic, but we don't have a really good understanding of those lifelong learning algorithms and how do they perform with changing distributions, with task switches, and so on. And the next part of the talk, I'm going to take a closer look at the lifelong learning algorithms with what we call as an interleaving learning setup. Right? We consider this as a more controlled setup, right? Because it is cleaner than what we presented before, which is trying to make it more realistic. Here, we are taking one step back and make the setup cleaner, right? And really understand what's going on when we have task switches going on. So, so this is the plot that we had for continual learning, right? So you have each of the tasks lined up in a sequence, and you learn task one, you're never going to revisit task one and again. Whereas a typical setting of human learning, right, you start with task one, task two, and then go back to task one, and maybe going to task three. So this kind of task increment and reviews and replays actually occur at the same time. Right, so, and also what's really matter in the real world is actually the current task performance, because it's kind of unrealistic as to assume that after learning, say, 100 tasks, that you still need to remember the first task. Maybe the first task isn't relevant at all in today's context, so it is actually more beneficial to forget these tasks. So what's really matters is the current task. But in the real world, there's always a task switching cost. Right, for humans, this has been found in a lot of psychology literature, right? When we try to do multitasking, right, we actually need to pay a cost by switching to a different task. So in the real world, it's always better to stay in one task for a little longer, right? So that you don't have to, you can compensate for paying that task switching cost. Right, so the question is that, does the neural network that we're studying, right, actually mimic the similar multitask learning strategy? Maybe for neural networks, it's also good to stay in task for a little longer and then transition to the next task, and then going back to this task for a review session, right? So do we need to really force our models to learn without having to revisit new tasks? So in the human learning literature, right, so we can also see that we do forget actually quite a bit, right? After just seeing it once, we can kind of forget a lot. And here, the forgetting was measured in terms of the time to relearn. And this is a famous work by Ebbinghaus in 1885 that studies the human memory and how much time it needs to relearn after studying a task. So actually, like the amount of time to relearn basically shows the amount of forgetting. So humans do forget, and then as we revisit the task more and more times, we actually start to remember it. So these experiments are primarily done by the first author of this work, David Mayo, which the work has published in the Coxsackie conference this year. So what we study is a very simplified setting where we split the CFAR10 data set into two parts, and each part contains 5 classes, right? So you can see this is like the IID setting is like you train on both tasks all together, and every step you get a mix of both tasks, right? And basically the red green showing the progress you get on each task, and the run length is the number of time steps you spend in each individual task. So as we increase the run length from IID to all the way to 15, you can see that each task starting out, there will be a drop of performance from you have left over last time, right? So for example, the green task, you basically dropped a little bit, But the interesting thing is, despite having quite a significant drop, which represents a forgetting, right? So your performance on the green task actually recovers really fast. So within the 15 steps, again, you actually quickly recover and then make quite a strong improvement within 15 steps. So the key takeaway here is that the forgetting is really large in neural networks, just like the human brain, but the recovery is even more dramatic. So the knowledge is not completely being thrown away. If it's being thrown away, then we would imagine after 15 steps, we would end up somewhat similar, or if not just a little bit better, right? But here it's actually way more better than before. So the knowledge is still implicitly being stored in the network. It's just that somehow in the outputs, it appears that as if it's forgotten, but it actually hasn't been forgotten. Another interesting aspect is that the world basically naturally provides us with data replay. So we don't actually have to design really fancy memory mechanism that holds on to the past data in the buffer and then do the replay, because the network can take advantage of that replay to consolidate knowledge. And what we see here is that basically the network in the end basically is going to converge to a multitask solution, and it will have less and less forgetting over time, right? But the interesting thing here is that with run length, for example, 15, we're able to achieve same or if not a little bit higher accuracy compared to IID with much less task switches. So this means that in the real world, if task switch gives you a penalty, then you would much better off doing more learning within each individual environment before you switch. So here is the diagram on the benefit of the run length, right? So basically we transpose this figure into this one. So this one is the number of steps within each environment, right? And this gray curve is the baseline of the IID. So you basically see that the first step, you get a big drop due to forgetting, but later you recover at around step 4. And then after step 4, you basically making improvement, right? And the improvement is getting bigger and bigger as you stay in the environment for longer, right? So, and basically what you found is that in the beginning, there is a little bit more forgetting going on, right? But during the middle phase or the late phase of the training, you don't get as much forgetting, at least on the evaluation accuracy or test accuracy here. So, and another follow-up work, this is done primarily by my students, Yan Lai, who is a PhD student at NYU here, is that we want to look at the scenario where we try to scale up the number of tasks or environments. So here we look at the question, what would happen if we have more tasks in the interleaving, right? So here we try experiments where you utilize large language models, and each task is basically a different article drawn from a news source, right? And these articles, basically you ask the language model to learn to generate the same words in the article. So the learning to do language modeling is the task here. And basically we learn from article 1 to n, and then repeat the same order again from task article number 1 to article number n. Right, so basically this is interleaving learning, but with more tasks, not just 2 tasks from before. So you would imagine that as we move away from the first task, right, the network starts to forget so that it can't generate the same words in the first task anymore. So this is actually what happens, right? So you have a sequence of 50 tasks, and you start training on task number 1 here, and every task we train on 10 gradient steps, so a run length of 10, right? And then, so basically you start from random. The task loss is the loss on task 1. You start from random, or you start from a pre-trained network, and then you train on task 1, so the loss on task 1 drops, right? And then it gradually goes up because you start forget task 1. So every single point here is after a single task, right, which contains 10 gradient steps. And now, after we go through an entire cycle of 50 articles, we go back to task 1, so it drops again, right? So everything looks expected. So now I'm asking you, what would happen if we train another sequence of 50 tasks? So what you imagine is that it's gonna forget again, right? And then going back down again once we see task number 1. But it's actually not what happened in reality. What's interesting is up to task 30 or 40, right? The task loss on task 1 peaked and then dropped again. So, and it dropped almost like over 50 or 60% of the forgetting before we revisit task number 1. So there's actually somehow the network learns to anticipate what's going to happen in task number 1. And by the way, all the tasks are randomly shuffled from the beginning, and this happens on any kind of random order of tasks. But the order from 0 to 50 and 50 to 100 is the same. Okay, so this is really surprised us. And this keeps happening, right? So like after you train on task 1, you get really good and you start forget, and then network knows almost certainly that this is going back to task 1 again. And this doesn't happen in the first epoch, right? The first epoch, the network just start forgetting from beginning to the end. So the first round is kind of learning the sequence order, but the second round and beyond is basically anticipating the order rather than just forgetting it. And this is a curve if you do a random shuffle. So note this is on log scale, so this doesn't line up very well with this plot. But you can see like if we randomly shuffle every epoch, so the 50 to 100, we get another order of the sequence, then you don't get the anticipation from the network, right? So basically the network is kind of memorized the order, right? Because we did the control here, which is randomly shuffling the task order every epoch. So does this happen on all networks? Is this a generic phenomenon? Actually, no, right? So like if we try to only train the top layer, right, there's no such effect. That's what we would expect normally, right? So you get the first task and then you start to forget. You see the first task again, you start forget. You see the first task, you start forget. So basically this cannot be replicated in a linear learning scenario. Right, and this effect will be stronger and stronger if you fine-tune more and more blocks or learning more and more blocks of your transformer. So this is really like a emergent behavior on the number of layers. So this is learning only the top layer, whereas this is learning the whole network. Right, you can see the shape of the loss curve looks fundamentally different from the two. And there's also another factor here is the model size, right? Not only the layers, but also the width, right? So if we only give it a language model of 70 million parameters, you don't really observe the same effect, right? And even to 160 million, this is still the same, right? It's what we had expected. But starting from 400 million and beyond, and some of the curve was on 1 billion models, it starts to have this interesting anticipation effect. So I think the reason behind the anticipation effect is still very mysterious, right? So this is something that only show up in a super large and deep networks, right? And we are only using a standard gradient descent. We're not using fancy optimizers. So this cannot be the memory effect of the momentum term in the optimization. So we're still looking for reasons to understand what's the underlying mechanism. But takeaway here is that even in such a simple multitask sequential learning, right? So deep network still gives us a lot of surprises in terms of its memorization forgetting. And we don't actually need to design super fancy modules, right, in these deep network in order to satisfy the certain learning paradigms like continual learning that we artificially designed, right? So by having this interleaving structure, although this looks pretty controlled, it's actually having deep network can basically learning this very naturally. And so we also wonder whether this phenomenon transfer to real world agents, right? And we hypothesize maybe highly likely it does, right? In terms of real world environment, and maybe using a large scale transformer to train on real world sequence of actions instead of sequence of word tokens. And before I end, lastly, I want to talk a little bit on the safety aspects, right? So a lot of people are concerned about lifelong learning because they are concerned about the instability in deployed product. And in fact, like the latest AI Act by the EU Parliament, they basically prohibit any like on-device learning on self-driving cars due to the concern that they don't think it's going to be safe. And this also applies to personalized AI, right? In the sense that if you want to have a chatbot, for example, to learn with your own conversation, right? This also gives a safety loophole for this chatbot to learn unsafe behaviors from the user data, right? For example, you have a released large language model and you do some personalized learning on your own conversation. Some of the conversation may be unsafe, may be toxic, right? And as a byproduct, maybe you get a large language model that isn't safe to use. So basically, the user data may contain materials that are harmful, biased, etc. So actually, in contrary to before, like where we want to memorize everything possible, here we actually want to utilize the custom data only in a safe manner by ignoring some of the unsafe data, but still making use of the useful data in the user-defined custom data. So the experiment we ran here is basically we start with a large language model, and then we start fine-tuning our user-provided custom data, which is potentially unsafe and contains biases, harmfulness, and so on. And then again, we fine-tune the model again on the safe and verified materials, just because we hope to bring this model back, right? So this is like the interleaving, but we're just starting with the two stages, tuning on user data and then fine-tuning it back on safe data. So you can see some of the larger models in the bias situation is that the larger model is actually learning the unsafe materials much faster than the smaller models. But after reviewing on the safe data, their bias goes down quickly, right? But one of the reasons not to do this review is that once you review on the safe data, you're going to forget all the useful knowledge from the user-provided custom data. So it's actually needed to basically have algorithms so that you can still leverage the useful part here. And by the way, this is a work that we recently wrote, a paper we recently wrote, and the first author is Jia Chen here, who did the most experiments. So what's interesting here is that instead of doing fine-tuning on safe data, we actually look at the example level forgetting on each of the examples, right? So after we fine-tune on safe data, right, the malicious examples learned before are actually forgotten at a higher rate than all the safe data or other irrelevant data points. So we actually plot here the horizontal axis, the number of training steps on the safe data again. So remember, this is the last stage where we fine-tune the model again on safe data. And here is the forgetting rate on each category of examples, right? So you can see the biased or toxic or harmful example quickly gets forgotten, whereas all the other examples kind of maintain their knowledge. And this is not very sensitive to the number of training steps. So that's actually something really, really interesting, right? Because the language model seems to differentiate different types of examples based on how much they retain their knowledge or memory, or how much they've forgotten the memory. So here, the forgetting rate is defined as 1 minus the recall of words in the original sentence. So you can think of this as a retrieval problem, right? The language model generates a bunch of words, and how much of these words are actually from the original sentence. And we can actually look at this phenomenon from a perspective of scaling, right? So we basically sweep from a GPT-2 medium model, which contains around 300 million parameters, all the way to a Llama 7 billion model. Okay, so there is an order of magnitude differences in the scale of the language models. And what's really, really interesting is that the smallest model actually show no preference on different data types, right? All data gets forgotten at the same rate. Whereas the largest model, the Llama 7B, shows strong preference on forgetting the unsafe data while maintain knowledge on the safe data. And this type of scaling effect is showing it again in this comparison of small and large models. And so towards this, we proposed a algorithm based on data filtering, and we call it forget filter, FF. So the idea is very simple, right? So we first train on the noisy data, and then fine-tune on the safe data, but we don't use the fine-tuned model, but instead we use the fine-tuned model to check the forgetting rate. Okay, so use the fine-tuned model to check how much you still remember some of the noisy examples. And we're going to filter out the examples that have a higher forgetting rate because these data are likely to be unsafe, right? So after we filter out these data, we're going to train again on the filtered data set in the hope that we can leverage the more useful data in the data set, right? Compared to if you just train on the safe data again, then you throw away all the useful knowledge. And this is the results. Right, so FF here is our forget filter algorithm. SC model is a self-correction prompting. So basically at test time, we give a prompt to the language model. Hey, please be non-toxic, please be friendly, please don't have any bias, and so on. Right, and you can also do a review, the safety review that we did before, which basically gets rid of the bias or the toxicity. But again, you don't get as good performance on a downstream task because there are useful knowledge in the user-provided data that you basically forget in the fine-tuning process. So you can see the FF algorithm or FF plus SC is going to get you the least amount of unsafe scores while still maintain the highest score on the downstream task. So this makes the algorithm really useful if you want to fine-tune your user data but want to stay away from the unsafe content. And this also has things to do with the long-term safety for personalized fine-tuning, right? So remember, in our experiment, we can do interleaving learning. So interleaving from unsafe and safe and unsafe again, right? And remember, in David's experiments before, that knowledge is not completely forgotten. It's just implicitly being stored in the network. So here is the curve of the unsafe score. Right, although it's being suppressed in the second epoch, in the third epoch, it's recovered again, right? Here, the recovery is actually bad. We want them to forget these unsafe examples. But unfortunately, the network implicitly remember those and recover even stronger and stronger. So this shows that just by doing one session of fine-tuning isn't going to erase this knowledge, right? What you really want to do is to do some sort of data filtering so that in the beginning, you don't learn with those. So the green curve is actually our FF algorithm, right? Where you do the data filtering and you never get a higher bias score as you fine-tune for more and more epochs. And even self-correction prompting is going to suffer from growing unsafetyness because of the implicit knowledge. So here, FF achieves the best in terms of long-term safety. So I know I'm running out of time, so just a summary of today's talk, right? So today we talk about lifelong learning in a structured environment, right? So traditional continual learning basically ignores the task environment structure in the real world. They basically line up all the tasks in a sequence and do not revisit again. Right, so here we are trying to explore the effect of doing it more naturalistically and to revisit those tasks and do interleaving setting. So in incremental concept learning, we propose a paradigm that's online continual and few shot. and we design a memory component that can help us consolidate concepts and can also be combined with self-supervised learning. And later we delve into the concept of interleaving learning, which we think is a more controlled experimental setup, so as for us to understand more about lifelong learning. And there's basically a trade-off between the current versus old task, right? If you stay longer in the current task, you're gonna do much better. And then you're actually doing better if you're fixing the number of task switches or if the task switch cost is high, right? And we have a bunch of new discoveries just from using deep network and stochastic gradient descent on those interleaving network environments, right? Where, for example, the anticipation effect is really intriguing, and we're still figuring out what are the underlying mechanisms. And in fact, forgetting is not all bad, right? So there are applications of forgetting, right, that can improve the safety aspects in lifelong learning. And I think that's really crucial for lifelong learning to succeed in real applications. And there are also a bunch of open questions, right? I think I'm personally very inspired to find out more about the answers to these questions. For example, how do we scale to more complex data, like having lifelong videos or dialogues? And there may be structural complexity, right? So for example, not just interleaving between multiple environments, but maybe having multiple scales of revisiting, right? And actually my collaborator, Matt Jones, had a iClear 2023 paper on having multi-scale structure environments where the structure follows 1 over the frequency types of autocorrelation noise. And there's also a question of how do we have better memory components, whether we want, say, like a stored memory or a more distributed memory storage, right, that can complement, the parameter memory in the model. And there's also a question of curriculum learning, right? When and why does curriculum learning help continual learning, right? Can we introduce the type of curriculum in the interleaving learning setup? And we want to be able to understand anticipation better in stochastic gradient descent and understand the trade-off of learning versus forgetting, and also understanding so many interesting scaling behaviors in forgetting and in continual learning of large language models, right? And these behaviors only show up in larger model, which makes us really interesting. So before I end, I'd like to acknowledge my co-authors and collaborators of the papers that I presented. And so there's a list of these people. And thank you very much for your attention. And I'd like to take any questions from the online audience.